In this video, we are going to look at hypothesis testing with contingency tables, which is a test for independence. So the first thing is to look at what a contingency table is. Sometimes it'll be referred to as a two-way table, but it is a table that has frequency counts for categorical data that corresponds to two different variables. So one variable will be like your row heading, and one will be your column headings. So an example of what this could look like is maybe we are looking at the different levels of class, so freshmen, sophomore, junior, seniors, and then we're going to look at whether they live in a dorm, rent an apartment or a house, own, etc., etc. So this is just an example of what a contingency table would look like. So as you can see in each cell here, there's counts for every single one of those categories. Now when we say we're going to do a test for independence, what we're really looking at is we're going to test the null hypothesis that the row and column variables are independent of each other. So in this example here, what we would be looking for is, does the grade level influence the living arrangements or vice versa? So we are checking, are they independent or not? Now, when we do this particular hypothesis test, it's going to be a chi-square test, and it's only going to be a right-tailed test again. And we do have some requirements that we would need to check. The first requirement is that we want to make sure that we have a random sample. We also need to make sure that our frequencies are expressed in the form of a contingency table. And then we need to find our expected frequency. We will again want to make sure that our expected frequency is at least 5 for every cell in the contingency table. Now, this does not necessarily mean that the observed frequency has to be 5. It's the expected frequency. Now, to compute our expected frequency, we use this formula here where it says E equals the row total times the column total divided by the grand total. And we will revisit that in just a minute. Now, once we check all our requirements, our null hypothesis is that the row and column variables are independent, and then our alternative hypothesis is that the row and column variables are not independent, or that they are dependent. To compute our test statistic, notice this is the same formula that we used when we did the hypothesis test for goodness of fit. So we're still going to be finding our observed minus our expected values, and then we have to square that and divide it by the expected values. And then we'll find the sum of those, and that will give us our test statistic. Once we have our test statistic computed, then we can go ahead and compare it to the critical value, which will be from our standard chi-squared table. Now, our degrees of freedom is slightly different for this one. We would take our number of rows minus 1 times our number of columns minus 1, and that will give us our degrees of freedom that we would need to look up in our standard chi-squared table. So let's go ahead and look at an example of how to do this by hand first, and then we will look at how to do it using technology. So let's say our problem is that we want to test whether or not a new medication was effective in preventing colds. So the table below shows the results of the experiment. And we're going to use a 0.05 significance level to test whether or not the drug seems to be effective to prevent colds. Now, the first thing we need to do is we're going to need to check our requirements. So the first thing we want to check is if we have a random sample. Well, we don't really know a whole lot about how they did this experiment, but there doesn't seem to be anything indicating that it's not random. So we're going to make the assumption that this was a random sample. So we're going to assume that when they were doing their experiment, people were randomly assigned to all of the different groups to make this a random sample. Our next requirement, we have to have the frequencies expressed in the form of a table. Well, we have our contingency table here, and we do have frequencies for every single area. And then the third one, which is the longest one to check, we need to make sure that the expected frequencies is at least 5 for every single cell. Now, remember, to do our expected frequency, we have to take our row total times our column total divided by the grand total. Now, in my table, the way it's set up right now, I don't know any of my totals. So I'm going to first have to find my totals for every single column and every single row and the grand total. And then I can go ahead and figure out my expected value for each cell. Now I'm just going to write down my totals at the end of each location. So my first row here, I would take 52 plus 24 plus 26, and that gives me 102. And then I'm going to do 31 plus 18 plus 24, and that gives me a total of 73. Now when I do my columns, I would take 52 plus 31, and that's going to give me a total of 83. And then 24 plus 18 gives me a total of 42. 26 plus 24 is a total of 50. And then my grand total I'm going to put down here in the very far right. If I add up my 102 and my 73, I'll get 175. Or you could have added the 83, the 42, and the 50, and you'll still end up with 175. So now, in order to find my expected value, I'm going to start with the cell that has the 52 in here. So it says I need to take my row total. Well, the 52 is in the first row, so I would take 102 times my column total. Well, the 52 is in the first column, so I would times that by 83. And then divide that by my grand total of 175. Now when I do that computation, I end up getting about 48.3. I'm going to put that value in parentheses over here so I can remember which value goes with each cell. Now I can either move to the 31 or to the 24, it doesn't matter. I'm going to do the 24. So now when I do my 24, I have to take the row total that's it's in. So it's in row 1, so I would do 102 times the column total it's in, which is 42, and then divide that by 175. And when I do that computation, I end up getting 24.5. So I'm going to transfer that over here. Now I'm going to do that for each of these values. I'm going to take the row total that it's in times the column total that it's in and divide it by the grand total to get all of my expected values. So here I have all my expected values entered in each of the cells in the blue. Now notice I did only round mine to 1 decimal place just so I could fit them in the cells. So we will probably be slightly off when we do our final computation compared to what the technology is going to give us. So you have to decide what is the appropriate amount of rounding for the problem that you are working on. So we've got all of our requirements checked because as I look at each of these cells, every single cell has an expected value larger than 5. So that final requirement that we were looking at, we're good to go with. So now I can go up ahead and set up my null hypothesis, which is going to be that the row and column variables are independent. Or it might be phrased to indicate that, getting a cold was independent of the type of medication they got. So it's going to be some phrasing. It can be generic like what I have here, or it can be a little bit more specific, but we are always testing in the null that they are independent. And then our alternative hypothesis is that they are not independent, or we could phrase it that they are dependent. Now to compute my test statistic, I am going to use that same formula we did with goodness of fit. So I have to take my observed minus my expected, square that value, and then divide it by the expected value. Once I get all those, then I find the sum of those, and that will give me my test statistic that I will need to compare to the standard table. So I'm going to set this up as in a table, kind of like we did with the goodness of fit test. So I'm going to do my observed minus my expected, and then I would take those values and I would square them, and then I would take those values and divide them by the expected value. Now here you're going to have to make sure that you stay very organized and keep track of which values go with each cell. So I'm going to start with the 52. I'm just going to jot that down off to the side there. Now, when you're filling this table out, you want to make sure that you stay very organized, because our expected value is different for every single cell. And since they aren't just in a straight line, we have to make sure that we know exactly which line goes with which expected value here. So I'm going to write my expected value for each one out in the front here, just so I can make sure that I keep it straight. So I'm going to start with my very first cell that has an observed value of 52 and an expected value of 48.4. So when I do 52 minus 48.4, I end up getting a 3.7. You know what? It might actually even be easier to just do this whole line first. So then I'm now going to take my 3.7 and I'm going to square it, and that'll give me a 13.69. And now when I take that value and I divide it by my expected value, so my expected is the 48.4, not the 52. The 52 was the observed. So I'm going to take 13.69 divided by the 48.4, and that gives me 0.2834 approximately. Okay, now I'm going to go down to the cell that has the 31 for the observed and the 34.6 for the expected. So I'm going to just jot down that 34.6 out front here so I remember which one I'm on. And now I'm going to do my observed minus my expected. So that's going to give me a negative 3.6. I'm going to square that value, which is 12.96. And then I'm going to take that value divided by my expected. So I'm going to divide 12.96 by the 34.6. And that turns out to be 0.3746. Okay, I'm going to move to the 24 and the 24.5. So my expected is 24.5. Well, when I do observed minus expected, I get negative 0.5. And I'm going to square that value, which is 0.25. And then when I divide that by my expected value, I get 0.0102. Okay, I'm going to go ahead and finish out my last three cells here. Okay, so now I've finished out my last three cells. Now when I come back to my formula here, it says that I need to take the sum of all those values I just found. So in my last column here, I need to find the sum of all of these. So I would add those all up. And when I add that up, I get approximately 1.473 or so. So this right here is equal to my test statistic for my chi-squared value. Now, once I have that test statistic, because we're doing the critical value method right now, now I need to go to my standardized table and I need to find my critical value. Now remember, my degrees of freedom though are the number of rows I have. So I have 2 rows and I have to minus 1. Then I take my number of columns I have, which I have 3 columns here, take that minus 1. So my degrees of freedom, I actually end up with 1 times 2, which gives me a 2. So I would use 2 degrees of freedom when I go to my table to find my critical value. When I do that, I find the critical value of 5.991. Now remember, the chi-squared test when we're doing contingency tables is only a right-tailed test. So my critical value of 5.991 is here. And then I look at my test statistic, which is 1.47. That's going to be down here somewhere. So my test statistic falls in the non-rejection region, so I would not have enough evidence to reject the null hypothesis, which means I am not able at this time to support the alternative. What that means as far as the problem goes, I don't have evidence to say that the different medication they were given was able to determine whether or not they were going to get a cold.